Hey, this is Horner, and we're looking at the 1998 Mechanics number 1 question for AP Physics C. You have a couple of gliders here. They're moving freely on the track, no friction. Glider A gives you the mass, and glider B gives you the mass. They move towards the glider. You've got a spring here. They use something called strobe photography. So the strobe here will flash at 0.1 second intervals, and so you can kind of see its motion as points in time. So it kind of tells you where these things are at time. The total here, it tells you that it's a total time of 2 seconds, and then it collides with glider B. So the diagram represents the motion of the glider. Positions of the glider at each 0.1 seconds are indicated by the symbol A against a metric ruler. The total elapsed time after each half second is also indicated. So determine the average speed of the glider A for the following time intervals. So these little tick marks tell you where the glider is. And you'll notice that as it continues to go, you can kind of see where it's at. So for the very first one, they want us to find the average speed from 0.1 to 0.3 seconds. So that's pretty easy to do. It's just speed is equal to distance over time. For this one, the very first one, we've gone from 0.3 meters to 0.1 meters, and we're going to divide that by 0.3 seconds minus the 0.1 seconds. So we're looking at this variable right here. And at this point, this is really easy. It's just 1 meter per second. For the second part, it's from 0.9. So we're going to look at it here at 0.9 seconds to 1.10 seconds. So at 0.9 seconds, we're looking at here's 0.1, 0.2, 0.3, 0.4, 0.5 seconds. Here's 1 second, so here is our 0.9 seconds. This is our 0.9 seconds here. We do see that we're starting there and we're going all the way over to 1.10 seconds. So this is 1 second. This would be the 1.10 seconds. And now we've got to figure out what these values are. So we've got, once again, V is equal to D over T. Our final distance looks like it is 0.99 meters, so 0.99 meters. Our original distance looks like it's about 0.87 meters, so minus 0.87. And they already told us the time here was 1.1 to 0.9 to 1.1. So when you do this, you end up with 0.6 meters per second. So already we can see that this thing is slowing down as it compresses that spring. For part 3, we're looking at the next instance here, and it's from 1.7 to 1.9. Here's 1.5, so 1.6, 1.7 would be this tick mark right here, and then 1.9 would be this tick mark right here. So you can see that it's really decelerated a bunch. Again, we have the average speed is equal to the change in position, or the distance divided by the time. So our distance here is about 1.18 meters, so you can look and see this is about 1.18 minus, and then 1.14 would be right here. And we're going to divide that by our time, which is 1.9 minus 1.7. I keep getting the times from right here. And so we end up with 0.2 meters per second. So now we have all of our times. We had 1, we had 0.6, and we have 0.2. And these are not times, they're actually speeds. So 1 meter per second, 0.6 meters per second, and 0.2 meters per second. At this point on the next page, they want us to use those times, and it says sketch a graph consistent with the data above for the speed of the glider as a function of time t for the 2-second interval. So once again, it's 1.6. So here we've got 1, we have 0.6, and then we have 0.2 meters per second at those various time intervals. Let's go ahead and draw this. So we're going to start at 1. We know that somewhere in this area we start, this is position 1. So here's position 1. Position 2 is at 1 second, and we know that it's about 0.6. And then finally, position 2 is position 3. So this is position 2. Position 3 is at 0.2 meters per second, so you can tell this is 0.2 right here, and our time for that one was somewhere in this area. So now we end up with a pretty much a straight line for constant velocity, and then at position 1 we get a curve that starts to slope down. We get a pretty straight line here for constant deceleration, and then we get this slope comes back, and then we end up with this final speed here, which we're going to mark over. And so now we can just say that this is section 1. We know that this is really, oops, this is section 2. And finally we have section 3, and this is for point 3. So there's our points, kind of what we're doing, so you can kind of see what it's doing. For the next part, they want us to try to figure out, use the data to calculate the speed of the glider immediately after it separates from the spring. So there's two methods to do this. Let's go ahead, since we're doing momentum, and use the momentum method. Obviously this is a elastic collision, and we know that the mass of A times the original speed of A plus the mass of B times the original speed of B, which is 0 because they've not collided yet, should be equal to the mass of A times the velocity of A final plus the mass of B times the velocity of B final. So we'll plug everything in. This is 0.9. Our velocity is initially 1, and that's equal to 0.9 times our final velocity, which is 0.2, plus the mass of B, which is 0.6, times the final velocity of B, which we don't know. If you solve for this final velocity for object letter B, you're going to end up with 1.2 meters per second. So you do get 1 point for the conservation of momentum and 1 point for the velocity at B. Because it is an elastic, just elastic collision, we do conserve energy also. So you could also use conservation of energy and you would end up with the exact same answer. Shouldn't be any different whatsoever. For the very last part of this problem, for letter, I'm sorry, this is for part C, letter I. They want us to graph the function of the speed of the glider as a function of time. So at this point we know that for letter B, so we're looking at glider B, we did glider A already. For glider B from 0 until 0.1, which would be right here, we don't have any velocity, so we'll put P1 here. We know that 0.2, it should have the velocity that the other one started with, so we're going to move this over here. So it's about 1.2, and we know that somewhere in between we had that intermediate velocity. So here we're just going to draw our line over, and then it starts to accelerate and moves up very smoothly till it gets to here, and then it levels off. So each one of these I would label this as phase 1, phase 2, and then finally phase 3. This would be our second point that we can draw here. And I think that should be it. So now we're done with part 2 of this problem, and we can go ahead and look at letter D for this one. So for letter D, it says a sketch of the total kinetic energy of the two glider system over the 2-second interval has the following shape. KO is the original kinetic energy of the system at time equals 0. So they want to know, is this collision elastic? And obviously we already said it was, so we're going to say yes. But they want us to justify our answer. And we know for elastic collisions, we know that kinetic energy, is conserved. So we didn't have any loss of kinetic energy here. You'll see that it did dip down, but then it came right back up to the original level. If there was friction in this or anything else, then it would not be a totally elastic collision, as your stuff would come off this way a little bit. Briefly explain why there's a minimum in the kinetic energy here, and it's mainly because the energy goes from an initial kinetic, it then turns into a potential and elastic, and then it is rebounded and it ends up being a final kinetic energy. And all this energy from the elastic that came from the kinetic is then transferred into the final kinetic energy. So that's really it. So as long as you drew this and just kind of made sure that they understood that this is elastic energy, then it totally goes into totally, so you might write totally converted. And then this one would be totally converted also into the UE. And that is the end of this problem.